Alright, after learning about these basic principles of weight and balance, let's take our steps towards actually understanding how do we calculate the CG of every airplane. The first thing that we need to know is how to calculate moment. This is a very simple calculation. A moment of any weight is the distance of the weight from the datum multiplied by the weight, or weight times arm is moments. For example, 50-pound weight kept at 100 inches from the datum has a moment of 50 times 100, that is 5000. Very simple. Now let's take a look at a little more complex or little more detailed example. In this example, you see that there are multiple weights around the fulcrum. Remember here, the datum is imagined to be at fulcrum. The datum is an imaginary reference plane which can be placed at anywhere. It depends on the person who wants to solve the problem. In this example, we have taken the fulcrum to be our datum. So every distance is measured from the fulcrum. This system is balanced because all the moments around the fulcrum balance each other. Take a look. The moment of this 50-pound weight is 50 times 50, 2500 pound inches or inches pound. Moment of this 100-pound weight is 100 times 25 inches, which is the position of the weight from the fulcrum. The moment of this is 50 times 100, that is 5000. If you take a look, 2500 plus 2500 is 5000, which is equal to the moment of the weight on the other side. And this is exactly what we discussed when we were saying that when children play on the seesaw is balanced when there is equal moment on the other side. Here we can also say that the center of gravity lies at the fulcrum. The center of gravity is nothing but the weight of the whole system acting at a point. Imagine the center of gravity of the whole system being at the datum produces the arm of the CG to be 0 because it is exactly at the datum. Hence, the moment of the whole system is 0 because CG is at arm 0 times the weight of the whole system, which would be 50, 50, 100, 200 pounds. Arm times 200 pounds equal to moment. Arm is 0, hence the whole moment of the system is 0, which makes sense because the system is balanced. Now let's try to answer this question. This is a balance problem. You have to use the same logic that you do here to get the answer. In this problem, we have a plank and a fulcrum. The plank is assumed to be 0 weight. It has negligible weight and hence negligible moment. There is a 50-pound weight kept at 20 inches from the fulcrum. There is a 30-pound weight kept at 15 inches from the fulcrum. We want to determine where should we keep this 100-pound weight so that the whole system is balanced. We can just use the previous example and correlate it here to get our answer. What do? We can answer this question in two ways. Irrespective of the ways we use to answer this question, the answer will still remain the same. You will find out, don't worry. In the previous example, we saw that when the CG was at the fulcrum, the moment was 0, hence the whole system was balanced. Let's try to find out the CG of the whole system. Now, how do we do that? We need to calculate the moments of each of the weights. To get the moments, we will have to get weight times arm for each of them. So let's get our equation. The moment of the 50-pound weight is 50 times 20, which is 1000 pound inches. The moment of this 30-pound weight is 30 times 15, which is 450 pound inches. The moment of the 100-pound weight would be 100 times x. Let's say x is the distance where it is placed. If you add all of it, the total moment is 1,000 pound inches plus 450 pound inches minus 100 times x pound inches. Why negative? Because if this is the datum, this side is taken to be positive. Now again, which side to be selected positive depends on the person who's solving. I want to take this side to be positive. You can do the opposite and try it on your own. The answer is going to remain the same. So now we add up all the moments, which will be 1000 plus 450 minus 100 times x. This should be equal to the moment of the CG. Now remember, the moment of the CG should be 0 because we don't want the system to rotate. We want the system to be balanced. And the datum is over here. Hence, if the CG is at this location, the arm of the CG is going to be 0. The weight of the CG would be the total weight of the system, which is 180. Hence, now the equation becomes 1450 minus 100 times x equals to 180 times 0. If you solve this equation, you would get this distance to be 14.5 inches. This answer will not change if you take this side to be positive and this side to be negative. Any side of the datum can be selected as positive and the other side as negative. Now let's see what the second way of doing this question is. This way of solving this question is more similar to the way you calculate your airplane's CG. So listen carefully. Alright, just like an airplane has the reference datum at a nose maybe or at the firewall, we can select our reference datum wherever we want. In this case, I select the reference datum at this end of the plank. Now the answer again should not change because it is still the same system. But the approach of the solution will be different. We still want our CG to be at the fulcrum. But for the CG to be at the fulcrum, the arm of the CG is now no longer 0. The arm is 20 because that is the distance from the reference datum. Alright, so let's get our equations together. The first equation will be for the 50-pound weight. 50-pound weight is at the reference datum. Hence, the arm of the 50-pound weight would be 0. So 50 times 0, we get a moment of 0. Second equation for the 30-pound weight would be, if you take a look, that is 20 inches, that is 15 inches. So in effect, the 30-pound weight is 5 inches from the end of the plank. The moment will be 30 times 5, which is 150 pound inches. Remember, now I'm taking all of this side to be positive. Hence, all my calculations would be positive. Then comes the CG. Here we have to consider the CG because the CG is at the fulcrum, which has an arm of 20 inches. The third equation will be the CG moment. The CG moment will be the total weight of the system 180 times the arm, that is 20, which is 360 and one more 0, so 3,600 pounds. The fourth equation would be that of the 100-pound weight. We still don't know where the 100-pound weight needs to be kept. So the 100-pound weight is 20 plus x inches from the reference datum. So the equation here will be 100 times 20 plus x. Right? Right. Now, this is where we apply our proper conceptual thinking. We know that the total moment of all of the weights individually is always equal to the moment of the CG. Yes? Yes, because CG is the imaginary point which is physically proven from where the weight of the whole system is acting. So theoretically, the moment of the CG should be equal to the individual moments of the system. So the moment of the CG which we got before was 3,600. Let's take a look. We add the moment of the 50-pound weight, which is 0, plus the moment of 30 pound weight, which was 150 pound inches, plus the moment of the 100 pound weight, which is 100 times 20 plus x, and we equal that to the moment of the CG. When this happens and you solve the equation, you get x equal to 14.5 again. You should get. And this proves everything that I have just said. You can take the reference datum wherever you want. You can choose the side to be positive wherever you want. As long as your concept is clear that for the system to be balanced, the CG should be at the fulcrum and the moments of all the individual weights must be equal to the moment of the CG. This last conclusion is very important for CG calculations in the methods that we will discuss later. Very, very important.